Good day, everyone. We are the Group 2, and today we're going to discuss evolutionary trends. This presentation was prepared by Paulo Luis Dacal, Shane Mariel Caba, Angelica Cabantac, Sheena Cabugnason, and Neil Carabantes.
Evolutionary trends is defined broadly as an identifiable pattern in which the overall evolution of a trait occurs in a given direction within a group for a prolonged period of time. An evolutionary trend can be either directional change within a single lineage or parallel change across lineages. In other words, several lineages undergoing the same sort of change. However, not just any change counts as a trend. According to the Oxford University Press in 2018, evolutionary trend is defined as a steady change in a given direction, either in an evolutionary lineage or in a particular attribute. Example, height of shoot. Such trends are often apparent in unrelated. The Titano reconstruction shown here range from about 55 million years ago to 35 million years ago. The cause of this trend is not obvious. It may be a byproduct of selection for increasing body size and or it may be a result of selection on horn size directly. Bighorn individuals may have had an advantage in butting contests for females as in sheep and goats. Brontotheridae, also called Titanotheridae, is a family of extinct mammals belonging to the order Pissisodactyla, the order that includes horses, rhinoceroses, and tapirs. Superficially, they look rather like rhinos, although they were actually more closely related to horses. Equidae and Brontotheridae make up the suborder Hippomorpha. They lived around 56 to 34 million years ago until the very close of Eocene. The most obvious question to ask first is whether a trend exists at all. This may seem straightforward, but the most reliable demonstration of a trend is one that includes detailed historical information that can be difficult to obtain. Comparisons of fossils and or inferences drawn from phylogenetic analysis are usually necessary to establish the existence of a trend, and these generally require considerable effort. As a result, there can be disagreement among researchers regarding the existence or generality of even the most widely studied trends, such as those involving increases in body size or, in short, trends cannot be assumed to exist but must be demonstrated empirically, no matter how intuitive their occurrence may seem. The figure reflected on your screen was first printed in 1903, depicting the classic trends in horse evolution, including increase in body size, reduction in number of toes, and increase in height of grinding teeth. The figure evidently is a trend toward increased body size in horses, but it is localized to certain genera and time periods and reflects increasing diversity rather than a strong global tendency across all lineages. If the increase of body size is evident to all horse lineages, then it is considered as global, but if it is only evident to one genus, for example, in the modern genus Equus, then it is said to be local because there are genus that have small body size, such as the extinct three-toed horse Nannippus. Anagenesis and Cladogenesis are two types of evolutionary mechanisms. Both anagenesis and cladogenesis lead to speciation. Anagenesis is the transformation of a particular lineage of organisms to a different state, which can be justified as a new species from its ancestral species, while cladogenesis is the splitting of an ancestral species into several new species. The main difference between anagenesis and cladogenesis is that anagenesis is a type of phyletic evolution, which occurs only within a single species, whereas cladogenesis is a type of branching evolution. In other words, in anagenesis, one gene pool is converted into another gene pool. In contrast, in cladogenesis, a single gene pool is split into several gene pools. An example for this one is the evolution of man. When the early ancestors of hominids and chimpanzees undergo divergent evolution, thus creating speciation and branching, it is considered as cladogenesis since it produces different lineages. On the other hand, anagenesis is evident in the evolution and development of the early hominids to become the modern Homo sapiens.
Once again, good morning everyone. My name is Shane Marielle J. Caba, and in this part of the report, we're going to talk about what accounts for the trend. There are three levels of explanation for large-scale evolutionary trends, and these are the dynamic, the cause, and the basis. But we're going to only to focus on the trend dynamics. Dynamic is defined as the characteristic of changes among component lineages or at smaller time scales that underlie a large-scale trend. It has two kinds, driven trend and a passive trend. What are these driven trend and passive trend? In technical terms, driven trends are those in which the underlying dynamic is homogeneous, whereas passive trends result from dynamics that are at least locally heterogeneous. In simpler terms, the dynamics of driven trends occur primarily in one direction and apply to most component lineages, whereas passive trends are the result of complex dynamics operating in different directions in different lineages or at different times. This figure is the basis for classifying trends as passive or driven. A trend is passive if the forces influencing change in lineages over time are heterogeneous, as you can see in letter A. That is, if they occur in more than one direction. If the forces are homogeneous or they operate mostly in the same direction, then the trend is driven, as you can see in letter B. To determine whether trends are driven or passive, we have to use these three tests. First is the test of the minimum. If passive trends are most often the result of an increase in diversity within a group that is free to expand in only one direction, then one might expect this to involve only changes in the average and the maximum. As such, the simplest test that can be used involves an assessment of whether there has been a change not only in the mean or the maximum value within the group over time, but also in the minimum. The figure you see here is the test of the minimum. This figure shows the results of computer simulations designed to illustrate passive versus driven trends as distinguished by the behavior of the minimum values of the distribution. In the passive trend, which is letter A, there is a lower bound to the parameter, and the increase in the average results only from an expansion of the largest value. In letter B, which is the driven trend, the increase in the average results from a directional shift in the entire distribution in which both the maximum and the minimum values increase over time. The second test of driven versus passive dynamics is known as the subclade test. It involves comparison of species from specific moments in time, rather than an examination of changes in minima over long periods. Therefore, an advantage of this approach is that it does not require detailed historical information regarding relationships among species. A similar method, known as the skewness test, incorporates a more detailed comparison of skewness among several subgroups within larger distributions and is designed to identify the relative proportion of driven versus passive dynamics in trends where both are at play. This is an example of a subclade test. Both passive and driven trends can result in a skewed distribution in which most species exhibit a trait near the low end and a similar number of species display much higher values for the trait, resulting in a long tail of a distribution at the high end. If the trend is passive, as you can see in letter A, and results from an increase in variance that is bounded at the low end, then groups falling within the distribution and away from this lower limit should not show a skewed distribution for the trait. On the other hand, if the trend is driven and there is some factor that drives increases in the trait, which you can see in letter B, Then groups not near the low or high end should nonetheless display a skewed distribution for the trait as well. Most powerful test of trend dynamics is one involving direct comparisons of large numbers of ancestor-descendant pairs. Such comparisons provide a detailed view of the directionality of each change that took place and can deliver a convincing determination of whether trends have been driven or passive and whether this has changed at different times or at different scales. In particular, this test is capable of identifying whether there has been replacement of lineages with different properties. The figure you can see here is an example of the test of ancestor-descendant pairings. Comparisons of ancestors with their descendants can be used to distinguish passive versus driven trends, so long as an appropriate starting point is selected. For example, choosing species B, which is a distant ancestor starting at very low complexity, would not allow one to distinguish between passive or active trends, as in either case its descendants will very likely be more complex than it is. However, choosing a species A, which is more recent ancestor and is of intermediate complexity, allows an informative assessment of the direction of changes among its descendants. In a passive trend, the number of A's descendants, which is you can see in asterisk, that are more complex than A is roughly equal to the number of descendants that are less complex than A. Both the average will still increase because there is a lower limit of complexity. In a driven trend, most of A's descendants, as you can see, the one with the crosses, will be more complex than A.
Good day, everyone. I am Angelica Cabantac. Now let's proceed to the three causes of trends, which are irreversibility, natural selection, and species selection. The first one is irreversibility. This is when evolutionary changes can only move in a single direction. So there are some traits that are so difficult to reverse that the value can only move in one direction. For example, once an animal lineage emerges from the water and evolves the ability to breathe air, it seems to be very difficult for that lineage to revert to extracting oxygen from the water. So shown in the picture, there's a tiktaalik, which is considered to be the ancestors of most terrestrial vertebrates that switched to air breathing. The second one is natural selection, which we are very familiar with. So natural selection can cause evolutionary changes in a lineage to be biased in a particular direction. So natural selection causes consistent change in one direction. For example, is the ammonites. So, ammonites is a clade of extinct mollusk with intricate many-chambered shells. So, as new ammonite lineage evolved, the way that these chambers fit together became increasingly complex. Evolutionary change in the direction of increasing complexity was consistent and may have been caused by natural selection, which favored greater shell strength. The third one is species selection. This is when a character causes a lineage to speciate more frequently or go extinct less frequently. There will be bias towards lineage that have that character. So the traits that increase speciation rates can produce a lopsided phylogeny as shown in the graph. Example for this is the marine snail. So marine snail lineage exhibit an evolutionary trend. As time goes by, we see more and more lineage with direct development, meaning that they do not go through a stage where their larvae swim around freely. Why might this be? If a lineage has direct development, its larvae don't disperse very far. They stick close to home and are isolated from other population. That means that if some directly developing individuals somehow ended up in a new place, they probably would not get to reproduce with their parent population. In other words, having direct development might cause the lineage to get chopped up into isolated subgroups, which might become reproductively isolated from one another. If direct development is indeed linked to increased speciation rates over time, we'd expect to see more and more lineage with direct development, which is now called the trend.
Good day, everyone. Now let's talk about the three trends in the history of life. The history of life seems to be characterized by three large-scale trends in complexity, and these trends seems to be connected with each other. The first is the rise in the number of levels of organization within organisms. That is, a rise in complexity in the sense of hierarchy. The second is the increase in complexity in the sense of differentiation, in the number of different part types within a level. The third trend is also in complexity, but it is a downward trend or a loss of differentiation at the lowest levels in organisms within its parts, and it is also called a decomplexification. The first trend is increasing hierarchy. Hierarchy is levels of nestedness, levels of parts within wholes, and trend 1 is the addition of successive levels over time. Figure 1 shows the trend in vertical complexity over the history of life, showing the first occurrences of organisms at each hierarchical level trend trajectory. So in this figure, the eukaryotic cell arose as an association of bacteria and therefore is one hierarchical level above a bacterium. A multicellular individual is one level above a eukaryotic cell. A colony or society is a level above a multicellular individual. There are some footnotes that are needed in order for us to understand more about this trend. First, this is a trend in complexity, but complexity in one narrow sense, hierarchy, or what it is called, vertical complexity. Vertical complexity is a number of levels, or in other words, the depth of nestedness. Second, the trend is only in the maximum. The highest level of hierarchy present in Earth rose with each transition, and a rising maximum does not by itself indicate the existence of any upward tendency. Third, the trend of transitions is reminiscent of the major transitions in evolution. However, they are not the same. For one thing, the transitions in hierarchy are defined consistently, all of them meeting a single common set of structural criteria. A second trend is the rise in number of part types or degree of differentiation among parts. The usage of the word complexity is increasingly becoming standard in biology. It is also been called horizontal complexity or pure complexity. Horizontal complexity is the number of different part types at a given hierarchical level. So the graph is reproduced here in figure 2. Consider just the first data point, the sponges. A modern sponge has about 10 cell types and its larger group. The sponges generally originated in the early Cambrian about 540 million years ago, so more likely a bit earlier, we now believe. In constructing the graph, the assumption was that the first sponges had about the same number of cell types as modern sponges. Other points are plotted using the same assumption. Overall, the graph shows a rise in the maximum number of cell types from sponges to humans. Now remember that horizontal complexity is always specific to a particular level, and so this trend tells us nothing about horizontal complexity at other levels it has. So the theory that predicts increase is called the zero force evolutionary law, or the ZFEL, which says that in the absence of natural selection favoring increase or decrease in complexity, the number of part types or degree of differentiation among types is expected to increase. This tendency, a kind of upward push, may or may not produce an actual trend. So the third trend is the complexity drain. At the same time, the complexity is increasing. a deeper current flow in the opposite direction. The parts themselves are getting simpler. As the cells of multicellular organisms are becoming more and more different from each other, the cells are losing part types as colonies are becoming more complex, as the individuals that constitute them are getting more different from each other. So the individuals themselves are losing internally complexity. Their complexity is being partly drained. Moreover, this third trend is a downward trend or a loss of differentiation at the lowest levels in organisms within its part. This is a schematic representation of the three trends which together constitute an evolutionary syndrome. The figure shows the transformation of a free-living lower-level entity, and it is found at the left, into a poorly individuated higher-level entity. So it is in the middle, and then into a highly individuated higher-level entity. So for the first trend, it is an increase in hierarchy. At the same time, the number of types of the medium-sized circle increased from 1 to 4. In other words, there was an increase in horizontal complexity. So in trend 2, an increase in number of part types. Finally, notice that the free-living lower-level entity on the left has 4 subpart types, the groups of tiny circles within it, with the 4 types distinguished by the 4 shades of gray. On the right, each of the 7 parts of the higher-level entity has fewer. So, for the third trend, the loss of subparts within the parts, and it is then called the complexity drain.
Why don't trends continue indefinitely? There are several possible explanations for why trends may be limited in scope. First, physical limits. Organisms are subject to various physical limitations that can place a cap on the extent of change that is possible. For example, land-dwelling mammals are probably limited to a certain maximum size by the effects of gravity, which is lessened in water because of the effects of buoyancy, and insects may be limited to a maximum body size by their mostly passive respiratory systems. Second, genetic limits. Consistent directional change requires the continual addition of new variation by mutation at the population level, by speciation at the species level. It is possible that at some stage the requisite mutations simply never occur and directional change slows or stops as a result. Third, ecological limits. In addition to limitations inherent to individual organisms, there may be external limits imposed by the environment. By way of example, larger organisms require more energy intake, and it is possible that this becomes impossible to achieve beyond a certain size. Next, reaching an optimum. In some cases, adaptive change may continue only to a certain point where an optimum is reached, beyond which any additional increase is less adaptive. Driven change, in this case, will occur only during the period before the point where this optimum is reached. Next, changing environments. Natural selection driven patterns will last just as long as the selective pressure persists. Specific selective pressures that cause directional change are often only temporary in a world of changing physical and biological environments. Next, organism level trade-offs. Trade-offs are typically described by negative phenotypic or genetic correlations between fitness components among individuals in a population. Changes to one feature almost certainly instigate correlated changes in other features. When changes in a particular feature begin to compromise the function of others, this may place a limit on further modification. Species level trade-offs. It's likely that directional changes resulting from short-term population level processes would have long-term implications for the species. For example, increases in body size may be favored within species, but larger animals tend to be less abundant and to have slower reproductive cycles, which can make them more prone to extinction. Lastly, mass extinction. Regardless of the trends that had been underway during normal times, the massive, mostly indiscriminate loss of biodiversity during mass extinctions may fundamentally change the distribution of species and halt, reset, or even reverse previous trends. For example, there appears to have been a trend toward increased body size among dinosaurs, but obviously, this ceased when they disappeared during the Cretaceous to Tertiary extinction of event. Identifying and explaining large-scale trends in the evolution of life is a significant yet difficult aspect of evolutionary science. Large-scale evolutionary patterns can be caused by a variety of mechanisms. Trends can be created by higher level processes, and they can be passive or directed, and they can be influenced by a variety of factors.